name's Tom Neen. As Emery said, I'm from Cisco's CTO office in the UK and Ireland, and I'm delighted to introduce this session, Data Has Shape and Data Has Meaning. I'll shortly introduce Enzo, who's from our Global Emerging Technology and Incubation Group, who look at all of things in the future. And Enzo is one of our kind of senior technical leaders in that group, and focuses a lot on things related to AI and machine learning. And actually, both of us have worked quite closely with the UCLA AI Center, which I think you know, Cisco was a founding partner. As data gets larger and more complex and more difficult to analyze, we have to kind of simplify and think about the different methods that we have available to us to actually enable us to make sense of that data in lots of different ways. So Enzo is going to talk to you about some of the new reasoning, some of the new topological based systems and ideas that base the analytics around kind of the shape and the nodal structure of the data, and using methods such as topological data analysis, or TDA, which some of you are probably familiar with. And I'm no doubt he will give you some amazing stats as well about the size of the data universe, which people are always trying to have a guess at. And I can't believe that that any of the figures are totally accurate now, particularly as we've gone through this period of COVID-19. I can only believe that that data universe is even larger than it's ever been. So with that, I'm going to hand over to Enzo and take it away. Thanks, Enzo.
Okay, thank you, Tom, for the introduction. So basically, this talk will be an invitation for thinking to different pathway that will solve the whole problem. What is artificial intelligence, and what is the objective of artificial intelligence? That is not for sure to take over the world and to kill all humans, if we're helping humanity. So basically, I will just show here the agenda. We will talk for the data dilution complex system, for the machine learning, deep learning in big data. The topological analysis will give you some background on the methodology, what the TDA can do with respect to big data, and a short discussion on what next. So let's start. So let's start really from square one. So the definition of AI. So if you look here, I put a definition, one of the many definitions. There's so many definitions, probably too many definitions of AI. And again, this is, say, AI variety of information processing technique and technology used for perform goal-oriented tasks, and the mean to reason in pursuit of that task. So this definition quite nice, but doesn't make any sense for the industry. You cannot do anything. So it's just saying that AI is part of IT processing. No, AI is quite larger than IT. You cannot reduce. So change completely the definition. So let's do this one. We human want to explore how machine, this objective, can acquire human-like communication and reasoning. Human-like, we don't want a machine that will do exactly. It should be similar to, but not exactly the same. And why? What is the objective? Is to gain useful knowledge. We don't want to have final knowledge to our question, kind of knowledge that could solve a problem. Which problem? Problem related to the environment and the capability to adapt to the environment. This is, as a definition, is a Darwinian definition. It's just saying that you need to adapt to the environment in some way. So, you know, Darwin was very clear. So among species is not the most intelligent and the stronger individual that will survive. Is the individual that will adapt. It's a matter of adapting. And adapting to what? To the observation, to what is happening now. You cannot acquire data to find out a fantastic theory. You need to find out the useful knowledge to survive to the environment. So the adaptation is the key. So the problem that we have in this world is the large scale data. Could be a problem, could be an opportunity. Let's say We have so many data, structure and structure, produce it any day, and it will be worse. So if you apply traditional technique for data mining, so they're not suitable to uncover the global structure. Again, you have a billion, we say zillion of data, but at the end of the day, you don't want to perform the examination of single data. You would like to have a global information. To have a global information, now you need to do either aggregate globally using a semantic ontology, either you are aggregating locally using the maximum likelihood estimation, or deep learning is aggregating locally. So if you aggregate locally, you miss the global picture. If you aggregate globally, you need a semantic ontology. A semantic ontology could be very good and interesting idea, but someone can give you the final ontology. Only God can provide the semantic ontology. So all other ontology are seed ontology that could be used for learning a new ontology. Again, so we are trying to here to differentiate what is the symbolic learning, symbolic ontology based, and the sub-symbolic. At the end, they're both wrong. So we need to find out a completely different methodology. The methodology, if you want to find out the emergent behavior, we need to find out a technique that will take into account the system in the globality. Let's see at the wish list. We'd like to have a large-scale exploratory data system and mining. We'd like to have to perform inferences and prediction on massive data set for predictive long-term planning. We would like to do early warning signal. So think a bit of the COVID-19. So probably we don't have exactly things for doing early warning signal. There are many, but not so evident. At the end of the day, we would like to reason on data. But if you think a little bit, what does it mean reasoning on data? You have the data, you have the data. You cannot reason on data. So probably you need to rephrase. So you need to turn data in useful information. So it's a transformation of data in something different. And the transformation should be general to represent the data of interest, not all the data, only the data of your small world, what you are interested in. So at the end, what we like to have is the ability to observe and adapt, again, adapt, in a way that human could not foresee. Think a little bit to have a high-dimensional data set. In the gene expression data set could reach 1,000 of the dimension. What does it mean 1,000 dimension for human beings that are good for 3 dimension? If you perform a dimensionality reduction, you're losing information. But if you're not doing, you're losing everything because we don't do something. So again, the methodology that we have are not adapted to this challenge. What does it mean? I said data. Data, this is for 2020, where data are coming from different sources. At the end of the day, at the end of the year, sorry, we would like 44 zettabytes of data. How on earth could you think to analyze 44 zettabytes of data? It's simply impossible. So let's see what could be a way for approaching the problem. We could use a methodology that comes from statistical mechanical space for what is science, that is experimental based. On the other way, you could use a real world space that is data driven. This is what the world is producing. In the experimental base, so let's use so your system, you are assuming that is ergodic. Ergodic is exactly what you don't have in the real world. Ergodic system means that in your phase space, the trajectory, it will inspect any single state. It's not true in the real world. You have non-ergodic system. The particle in our idealized world are all identical particles. In the real world is large, not infinite. Large, lot of particle, but is not infinite particle. And the particles are different, are heterogeneous. So things you can think of crowd detection. The people that are you cannot idealize as a boson gas of people that are interacting It doesn't work in that way. It's more complex. At the end, experimental based, there is a structure, a dynamics, in the real world, not representable by vector space. When you are using your feature space, your vector space for providing the input for the machine learning system, you're already forcing to the format that is not natural. So again, question, the method that you have are good enough? Let's see. Let's talk for the method that we have. These are a bird view vision of for 1940 to 2020. I will add some other method, but it's all the method that you have, not so many. If you look at the last method was support vector machine. So neural network are very old, and in the 40, not new. Deep learning is here, 2000. I could add, just to be fair, the variational adversarial engine, the GAN, the generative adversarial network, and the transformers that are just improvement of optimization, nothing really disruptive. Limitation. When you say limitation, I'm not saying that what you have in machine learning deep learning is not good. It's very good. We have the fantastic advancement using machine learning and the deep learning and high performance computing together. But there's still open question that we need to address. So one limitation is everything is a tensor, and the computational graph abstraction is what you have. The computational graph abstraction is what you have in all deep learning framework. Very powerful, but very limited. So here you will see an example for what is we call the elemental mul, add, and div for a simple arithmetical operation that you can extend. It's very good, very powerful, but it's a limitation because it's assuming that everything can be represented by a tensor. Supervised learning, very efficient, but need a lot of data to be trained. And at the end of the day, if I ask you who will annotate, is a human that will annotate. So you have an external oracle that will inject semantic information to your system. Otherwise, your system will be completely blind, no way for doing anything. And then when you are injecting a annotated sample, basically the sample are proxy for a class. So this is becoming quite weird. So the architecture of deep learning is opaque. Models are difficult to explain. So basically you cannot explain. Even if you try to explain, you cannot explain a system that has billions of nodes. So it's beyond human understanding. Ineffective to adapt to the unexpected event. Again, because you are training on a very particular set, so you cannot explain, you cannot expect that the system will be affecting on unexpected events. Lack of contextual abstraction reasoning. No one was requiring to have abstraction reasoning, so the lack is implicit. Good for local generalization, quite good. Again, bad for global. So there are kind of hybrid architecture that will put together sub-symbolic and symbolic, try to introduce the ontology on top of the deep learning system. So what they call the neurosymbolic learning. Again, quite old architecture that could not solve the problem, the challenge, or the problem that we have nowadays. So let me just recall this sentence for Judea Pearl. Data science is about interpretation of data. Data alone are hardly science, how deep you go. So at the end of the day, it's not a problem of volume of data and to be able to go down, to dig to your data. Is a problem of the complexity and the structure of the data that you have. Even the 44 zettabyte is not a problem to have a volume of 44 zettabyte or even bigger. The problem is the structure and the complexity of the data. We need a way. We need to find out a way to extract the structure of the data. At the end, we can ask, but this is just for the discussion. Do we need probably a completely different science for the big data? Now you understand that when they say big, I mean complex data. So where we are swimming in sensor and drawing in data. So this is what we will really worsen with the IoT and everybody connected. So with a really billion of equipment connected, so it will be very complex. At the end, the insight will be born from data, not born from theory. So we don't need really a theory, but we need the data as the data are coming, because the data and the relationship among data is what is important. So that give me just some background very fast for the different kind of reasoning that we have. I put on the right the Peirce triangle that will put together the inductive, abductive, and deductive reasoning. What we wanted to discover, think neither new, so this is a typo, neither new nor expected. And see the relationship and connection among elements. This is what we would like to achieve. We have data, but we are really not really interested to the data, because we are interested to the global vision that are based on the data. So the deductive reasoning, so the model-based system, tell us nothing about the real world, is for self-consistency. So deductive reasoning and the discussion about the causation is not really interesting to have a causation. Correlation could be fair enough if you know that is limited. So probably better the abductive reasoning, that is inference on the best explanation. Again, inductive and abductive reasoning lead to permanent learning. Why? Because they are incomplete. They produce an imperfect and useful knowledge. Think about it, it's exactly what as human we are doing. We are not starting from a theory. We are doing correlation, probably wrong correlation. So just to, even Newton was exploring astrology, and doesn't make any problem to him exploring astrology. Astrology was quite good at that time for doing correlation. Not now, we have astronomy, that's for fun. At the time it was very important. So at the end, let's conclude with this sentence: essentially all models are wrong. So again, don't try to train the best model in the world. Your model is wrong by definition, but are useful. Again, models are wrong but useful. We would like to have a model that are able to adapt to the system without the need to retrain always and always. Let's introduce topology. This is just to see what means for a topologist a cup, a mug that is a donut. So it's the same. So you see, starting from the cup, different deformation, different modification. So at the end, you end up with a donut is exactly the same. So for the topology perspective, you can eat a mug and drink a donut. So not really a problem. Let's see what does it mean. So I will start with Christian Siemens, a great topologist. In 1966, he came out with this very interesting schema. From one side, you put on the left quantity, on the other quality. Quantity is what we are doing now with engineering, with our system, with our metric system, with our measurement. So when you quantity is for prediction, on the other side, the quality will give you explanation. Quantity is for analysis, but quality gives you synthesis. Quantity measurement, on the other side, we have shape. Quantity is local, quality is global. So forget quantity, let's look at only quality. Let's do a science based on quality. The solution are found in algebraic topology. Topology is a very old, very old branch of mathematics, starting in the 18th century for Euler, Riemann, Betti, Poincaré, Morse, and many others. Is a formula for measurement and representing shape under continuous deformation. Geometry and topology, natural tool for handle high-dimensional complex spatial data. Okay, this is exactly what we are looking for. We have a complex spatial data. We need a way to handle this large data set. Algebraic topology, ignore local variation and capture global properties. Exactly what we wanted to have. So we don't need a new science. We need to use topology, algebraic topology, and all the different flavors. What is very important is sound theoretical foundation. That is not what what deep learning has. Deep learning is being put together by practitioners. I'm not blaming practitioner, but at the end we don't know what it works. You know, deep learning works until it fails, but it works. So let's start from an explanation. What I'm looking for when they say shape as meaning, which encode information. I give you a simple example. Imagine that you have a cloud of points together. So we are not really interested to the cloud of points. You would like to have an organizing principle for organizing this cloud of points. It's a straight line, it's a regression line. I don't need exactly the least square approximation for the regression line. It's just a line. It's enough to me to say I can organize all different points around a line. Second example, you can organize everything around a circle, give you periodicity because you're a circle. Here you have free group. Okay, sorry. You can organize around 3 different clusters. That is the organizing principle. This one is a branch or bifurcation. So at the end, you can use a topological descriptor. It could be a line, the clusters, the circle, the Y shape for doing inference and comparison. At the end, we are not looking at the data are produced, but at the organizing principle that will bring it together. It's a summarization of the original data. Topological data analysis started from Goodman Carlson, so it's quite recent. So Carlson is a topologist, by the way. It's an emerging method for analyzing large-scale data using geometry and algebraic topology. The typical pipeline, the data set are converted into a topological space. So we are not interested in the metric space. So it's a topological space in which you have a cloud of points. The high-dimensional information are discovered through a sequence of approximated topological space. Technically, the sequence of approximated topological space is called a filtration over simplicial complexes. Building a filtration is just looking at lengths for examining the data. When you say examining the data, you are examining the data in the high-dimensional space where the data are. We are not reducing, you are not assuming a manifold at the low dimensional dimension. We are not projecting at the low dimensional. We are using a probe that will inspect the data in the high dimensional space, and then we are projecting a graph that is giving us the relationship about the data, the high dimensional data. The filtration basically will extract different information from the topological space. So the idea behind is a deformation invariance. Of course, we are in a topological spaces, so the different letter I put here are exactly the same. So no problem. So for the different shape, A is always A. You can write in any different way, but it's still a way. So very robust. Coordinate invariance. So this, from the topological perspective, this is in 3-dimensional. Is a circle in 3-dimensional or 2-dimensional perfect circle almost a circle has absolutely the same shape. Compressed representation, a perfect circle made of 2 billion points together, it can be represented by 6 connected points. They are topologically exactly the same. Let's introduce the persistent homology. I give you example. So here for the mathematical definition is a summary of homology at the scale for a different filtration. The filtration can be represented in this way, where you have inclusion for what is called the persistent diagram. The persistent diagram will give for non-k-dim homology class. Basically, they say that there is a pair, epsilon 1 and epsilon 2, we say born at the one dimension and dead at the other. I will come later for providing a real example. What I want to say here, that the n-dimensional homology, it will count the number of holes, what is important in the topology, and what is important is the nothing, is the hole. So basically, in this example, not all the cloud points over there important. What is important is the empty space in between, the hole. So this is it will have a one-dimensional hole. Basically, the zero-dimensional is account for clusters. Cluster is a connected element. The H1 is accounting for loops. The H2 for voids, and so on. They say about simplex and simplex complex. The zero simplex is just a dot. The one simplex are two dot connected. The two simplex just a triangle, and so on. So all void. So basically, the simplex complex is a collection of simplices. So it's a generalization of graph. There are different ways for building it. Say put the Vectoris complex. There are other ways for constructing your complex. We will see, for instance, here we have you can represent by a graph, and the graph it will bring all the information represented by the original. Let's say with an example, what does it mean performing a persistent homology? Let's start with 4 dots in a two-dimensional space. Nothing changes if you go in the high-dimensional space. In the two-dimensional space, you start with 4, for instance. Let's build a two-dimensional ball. So this is a cycle, or radius d0. Nothing changes. We have still 4 separated elements. Let's increase until they connect. When they connect, I can connect the original dot and at the radius d1. So at the radius d1, I say the simpliciter is born. So it appears at a particular radius. Let's go on. I will go on until the hole that is born over here at radius d1, it will disappear. It will disappear at radius d2. So this is exactly the representation that you will have. We born at d1 when the elements start connecting. So this is the first connection, the H0. And they will disappear at the radius d2. If I increase, the same, disappear. So I can put all this information together in the single bar. The collection all bar will represent a barcode. Just give you a more complex example. So with this cloud point. So in the cloud point here, you start connecting. So you can start extending with a ball for each dot. You will see they will start connecting, but they're still separated. you can connect everything at this radius. So you have one is born and the other as well, the two holes. At this radius, one hole will disappear, the other will still there. So you go on until it will disappear. You put all this information, the persistent diagram. You have here the H0, the homology, zero-dimensional homology that will represent all the connection that you are able to perform. And one the first hole appear, and one the second and disappear, and one appear at this radius and will disappear at this one. The second one is appear at this radius and will disappear at this one. So at the end we have two holes exactly that will represent the Betty numbers, and will provide the summarization of the original data set. I will put here only one theorem that is very important because, you know, in the deep learning, machine learning, you need to be very careful about the noise injected. And if you modify a little bit, think at the adversarial example in deep learning, you modify some pixel and you have a misclassification immediately. Then you need to retrain with this one. So it's not a way, because humans are not fooled in this way, but the classifier are fooled because they pretend that the data are very stable. It's not the case for topology. Imagine that you have a clown point that will provide perfectly a cycle. If I do the persistent homology for this one, I will have one connection because they're already connected. So you will see the H0 for the connected point, the H0 homology that will be here. And then the H1 homology, it will appear and disappear. It will appear at this radius and will disappear immediately. Immediately after. At the end, the persistent homology represented will be simply 2 dots. Question: what can happen if I introduce noise? So I introduced a lot of noise around the original cycle, and I did the performance analysis on this original one. So you will see there are kind of connection that will be represented, but nothing that really changed the original organization of the persistent diagram. And the H1 homology that will move over there. The H1 point over here on the diagonal at what we call the topological noise. It can be removed easily because they are representing the loop that can burn and die immediately, but not representing the real one. The real one is stable. So the robustness against noise is really well represented. If you think to do a clustering with a traditional methodology using this cloud point, it will be very difficult that you find out that it's just one representation with a cycle. The persistent homology, you will see, it will give you the representation with the Betty only one hole as it is. So this is a pipeline, as we say. You start with input data for different origin. You build a point cloud. You build the simplistic complex, very different. I talk about the divisory rips, but are different simplistic complexes that can be built with different properties, different way for inspecting the data. Then you can create your using a different framework, your barcode for the persistent diagram generation. This can be used for doing a feature selection or measuring the performances of your system, just introducing some computation. So It's true that you are in topology and non-metric space, but you can keep your topological space with a metric space, so the Banach space. So this is possible. So at the end, you can have a Wasserstein or bottleneck distance that will be used for measuring the similarity or dissimilarity between two different persistent diagrams. For time series, it will be really tricky because time series need to be transformed in point cloud. In order to do that, you are using the Tekens theorem for the time delay embedding, and you are converting the Tekens in the point cloud in this phase space. Okay, once you have a point cloud, you can go on for the persistent diagram and Wasserstein distance for the similarity estimation for instance, you want to check two different time series, or you want to have a sliding window among a simple data time series in order to identify a change point. The second method for TDA is mapper. Mapper will create intrinsic simplicial complex model for multidimensional data. It's a three-step method. You need to define a filter function, you construct a covering, and then you apply a clustering. Let's do an example. You have a point cloud like this one. Now, you need to define what you want to inspect. So I want to inspect this point from the y coordinate. So I want to see how the system will be if I project that on the y coordinate. For instance, this is a defining what is called the filter function, a filter function for y coordinate. You can use different filter function. A PCA itself could be a filter function. Then I will define a number of covering. So here there are three covering with a 44% of overlapping. The covering will split the original cloud point in three different cloud points. So you can do in parallel. So the point cloud, each of them can be clustered. Now, if the cluster are, because of the overlapping, are something in common, you are connecting the cluster with an edge. So the edge connects a similar node, the node group or similar object. The color are depending on the color function, and again, it's up to you to define how you want to call it. Coloring is your probe, the high-dimensional probe that you are using for inspecting the high-dimensional space. The graph that you have is what you have at the end. So here, very simple, because you have a two-dimensional dot cloud, so you can connect one-to-one. You see the first node will represent the first segment here, and what is important, you have a split because of the two different direction of the point cloud over there that is represented by a common node for the two different directions. But nothing, no edge will connect the yellow and the green over here, as is nothing will justify this connection. So the pattern that you have, we call flare loops on bifurcation. So they're very important because flare are something that dissimilar to the general perspective. The loops are periodicity, and the bifurcation are things that are diverging. So this would be very useful for doing a similar feature selection. You can select features that belong to the different clusters that will best represent the original cloud point. So just an example that I did myself using 27 million data point in R 2000. So it is very high dimensional. Here represented 4 time series from this one. This is okay. If you see the time series that you can analyze individually, I want to like to have the high dimensional representation and not the individual. So doing the mapper, you see fantastically, it will split into. Wow, it's really strange. Why is split it into? At the end of the day, it's split around the July 4. You see, July 4 is quite It's important for the US. So something happened to the data center on July 4. The system say July 4, the system is moving to one state to another one. It's simply impossible to detect that this glitch on July 4 is representing a state change in the system. Now, I knew that there are two missing points over there. They are missing points because in those days, nothing was observed. Nothing was collected. Nothing was collected, you see here. July 26, 27, nothing was collected, is a flare. It's just putting aside. All the information are over there. Then there is a split. The split that will represent the different states. Overall, 27 million points in 55 seconds to do all the analysis. At the end, again, TDA for big data will be for complex data. Just to resume, complex system, emergent behavior, global behavior, TDA. This is the pipeline you need to go. Problem solved by TDA. Description of dynamic multi-level multi-scale complex system for using algebraic topology. Powerful tool for finding structure in data. So it's big in sense of complex. I mean, it's more for discovering inferences, procedure, and it's very robust to noise. Synergy for machine learning, deep learning. So it's not separated to deep learning. It can be used with deep learning. The process is called featureization. You can use the output of the TDA, for instance, a mapper. It can work together with a deep learning classifier in order to perform a feature selection. Improve supervised learning and improve even unsupervised learning in this sense. Customer benefit ability to obtain useful knowledge. Again, a customer is not really interested to have information on this single data. You want to have a global information. Global information, it can be provided by mapper algorithm. The mapper methodology can give you the global information that you need. Why? Because the output is a graph. A graph is very simple to be inspected. It can give you explanation. It can give you insight, real-time business for predictive planning, again, because it gives you global information. Ability to use model for large amount of data, and the feature summarization, again, because in using topological method by the methodology, we are moving from local to global. A lot of different applications. There are a lot of applications in bioinformatics, as you can explain, in forensic, in economics, early warning detection, anomaly detection, emergent threat detection. There are a lot of things related to explainability in the AI as well.
Enzo, I'm just giving you kind of 5 minutes.
Yes,
we've got quite a few questions coming in.
Last question, perfect. What next? What next? I will put just for give you a taste. What next? They're very fantastic. Topological data modeling. You can use topological framework for integrating semantic information sources. What is really more important? Topological signal processing, Robinson, that will provide a solution for heterogeneous sensor fusion using a chef theory. A chef basically is a mathematical data structure for storing local information or any kind of local information. And basically you are defining function not everywhere, but on open set. And it will give you information for global inference. What is important, just one line, the topos theory for Alexander Grothendieck, that will incorporate thinking, perception, and logic. At the end of the day, I start, where is the logic? The logic is in the structure of the data. You can reason on the data because the data has structure. The structure of the data is what you can allow you to do inferences. The logic is part of the topos theory. The topos theory is what we need to go for solving the challenge of the problem that we have. Take away swimming sensor drawing in data. Reasoning is possible because data is shape and shape has meaning. TDI discovering new insight in corpus data. TDI and deep learning better together. I finished.
Enzo, that was great. Thank you very much indeed. And as you can expect, well received and lots of questions. So I'll rattle through them as quickly as I can. I hope I can get through most of them. So probably quick fire answer so that we can answer all or a number of the questions that have come in. But first question that came in was actually, can you explain what do you mean by deep learning works until it fails? Because this could be said about anything, arguably. A quick answer to that one?
Yes, it was just a provocation. So deep learning work very well, but when you say you work until it fails, think about adversarial example. You train your system is very good for classifying your input. Then you are slightly modifying one input and your classifier fail. So okay, you can retrain your system because it's failed, but again it will fail again. So you will never have a model that will never fail. It will fail always in unpredictable way, and you need to account for risk, for minimizing the problem that you have when your classifier is failing. Think again for a face recognition when a human is misclassified as an animal or something not human. So this single human will sue you. So this will be really problematic for your system.
So fail and modify. Next question. Thank you. This is great. This is from Faiz. Is this also called non-Euclidean geometry? What are your recommendations to formally study this field, as it seems to me a master's in applied maths may be needed?
Yes, it's correct. I'm talking about graph and trying. Implicitly, I'm talking on non-Euclidean geometry. Non-Euclidean geometry is what you need to go. And I'm talking about topology, but the topology will go hand in hand with a non-Euclidean geometry as well.
Great stuff. I can answer this one because it says, would it be possible to show the definition of mapper again? This session's been recorded, so I think that the organisers, Emery and Adriano, will make this session available from Enzo. So yes, the answer to that is yes. The next question is, thank you for this great talk, but what tips do you have for non-mathematicians who use TDA-based tools? As an example, I use mapper-based TDA in microbiome research.
You can use, there are very good framework now. I can, for instance, there is Giotto, from ETH in Switzerland. There are Goody, there are Ripser. So, I mean, there are a lot of framework. You don't need to go deeper in mathematics and topology. You can use from a practitioner standpoint as well. So because of the very good framework that are available right now.
Okay, and then this one's from Dominic. It's a longer question, so just bear with me. I'm a bioinformation and have used similar examples to this. For example, use the UMAP algorithm for dimensionality reduction visualization of high dimensional biological data sets. One problem I get in practice is that several parameters must still be chosen to create UMAP representation. For example, we must choose the dimension of the space we project high dimensional data onto. We must also define the number of data points we consider neighbors of each data point. It seems like this information should be intrinsic within the data itself. Are there ways we can learn the intrinsic dimension of data in an unsupervised manner? And also real-life examples present data points which may have different intrinsic dimensions within the same data set. How do we deal with this?
It's a great search. Great search is a way to go for in order to find out the best choice. So it's like AutoML that you're using for tuning the hyperparameter for the deep learning system. There are tools that will provide kind of meta learning that's gone that way, that will provide the selection of the different parameter that you have to choose. The try and error is quite consuming, or you need to be to have experience on what you're doing. So grid search is a way to go for checking automatically the different combination for the parameters that you need.
That's a great answer. And then this is a more humorous one. The Innovate or Die logo, is that not from Blockbuster Video? Which I think they probably spotted your sense of humor there.
Yes, but this is my motto. I like a lot because I'm in innovation. I spent all my life in innovation. I'm still alive, so still I innovate a lot. I pretend to have innovated a lot. So I think this is a challenge for young engineers and the people. So you need always innovate. As long as you are innovating, you are alive. So otherwise you risk to pass away only because you stop thinking. Innovating is thinking, is what is important for the human being. So innovating is thinking to alternative, not the best, but something different. Then you discuss with the other guy, and then you will see how your idea will contrast them. So it's a way for communicating with other people. So this is again a great point, because AI is not something that can be built by a single genius in the world, but would be produced by a community of humans together with a common objective. It's too complex, AI, because there are too many domains that cannot be it cannot be learned by a single guy. So it could be people together that will provide the revolution, and the revolution should be the AI and the integration with the machine.
No, amen to that, and that's why things like the UCLA AI Center exist, and the community that's built around it.
Exactly.
I think the last question, but we'll see where we get to. Eva came back with another question. Could you go into a bit more detail on using TDA output as an input for ML/DL?
Probably, and we're not here. So let's check. You can use, for instance, you can use the Wasserstein distance. So, for instance, here you have a time series. I'm using a sliding window. For each sliding window, I use the persistent homology. In the persistent homology, I can compute a persistent entropy or the Wasserstein distance between two different sliding windows. This will be one measurement. I will create a different time series that it will made of Wasserstein distance or performance or entropy distance that can be used as input for a regressor. This is for answering the regression quiz. For the classifier, I can imagine that you have a cloud point. I use the mapper. I will use the ground truth for coloring the node. And then depending on the node, imagine that I ground truth saying bad, good, 1, 0 for malware, non-malware. I will color all the graph red and green, bad, good, and I will select the features that are on the flare, that are representing better the overall feature that you have. So this will be, what are the features? Are inside the node. In each node, you have a set of common features. I will select only those features that are important. This is part of the featureization, going through the mapper and the ground truth that will be used for coloring the graph.
That's great. And I think, Enzo, that has exhausted all the questions that have been asked. I'm sure there are some more, and I'm sure there'll be ways that Adriano and Emery will be able to get questions to you that can be taken offline. But I think from on behalf of the organization, the event, and certainly from me, from the Cisco side and the Cisco partnership in the AI Center, I'd just like to say thank you very much, Enzo, for such a engaging and thorough presentation and session that you've run today. So thank you very much.
Okay, thank you for the opportunity. Okay, thank you to all.
Open.